In this video, we will derive an expression for ratio of belt tensions. Okay, so we know the tensions here. There are two types of tensions created in the open belt drive or cross belt drive. So one is tension in tight side and one more is tension in slack side. So we need the relationship between these two in terms of the contact angle or something that we will derive later here. So before we derived an expression for length of the belt in the previous video and what is the power transmitted by the belt, in one more video we derived all those expressions here. So now today we will derive what are the expressions, the relation between the T1 and T2. Okay, for that first we need to consider the follower. So this is the follower here. Here the driver is there, one more driver is there. Now I took only one portion, that is the follower pulley along with the belt passing onto it here. Okay, so first consider the follower. This is the driven, I written here, follower pulley rotated in clockwise direction. So here I am giving the I given already the direction here, it will rotate in clockwise direction. It means driver rotates clockwise, driven also rotates in clockwise direction. Okay, this is shown in figure here. Okay, so T1, as we derived in previous video, the T1 is, it will comes under downside here, the tight side. T1 is tension in tight side, that we denoted by T1, and T2 here, this is the slack side. T2, this will be the tensions here. Just I'll draw the full driver and driven. We'll come to know here how the tensions will be created inside the belt and inside the pulley here. Okay, so if you take the open belt drive here, so this is the driver and this is the driven. So as we know that if the driver rotates in clockwise, driven also rotates in clockwise direction, and here we are pulling, so here tension is more, that is called as tight side tension. It is denoted by T1, and here it is T2 here, T2. So the direction of the tensions is like this here. Okay, like this. So follower side, these two directions T1 and T2. So driver side T1 and T2 in this directions here. Since we are considering only the follower, how are the directions here? Arrow mark. So here this is the arrow mark, here I denoted here. The same in the T1 side, the arrow mark is in this direction here. Okay, so these are the notations here. Next, what is theta here? I denoted theta here. Theta is angle of contact. What do you mean by angle of contact? The belt touches the pulley. So suppose the belt comes and it will start, it will contact with the pulley, driven pulley from A to B. Only this is the contact area, and from B it will leaves, and from A it will leaves here. So whatever the angle made by this in between A and B, it is called theta here. So contact angle. So angle of contact. Theta is angle of contact, that is angle subtended by the arc AB. This is the arc AB along with belt touches the pulley. So belt only touches in this arc here, AB. So this is the theta here. Okay, these are three notations, T1, T2 and theta. Now we will make some construction here. So we will consider only small portion of the belt here. First I will consider only small portion of this part, AB. We will derive the equation in this portion, then after integrating we will get what is the tensions in AB. Okay, so consider a small portion P and Q here. Just I am taking here P and here Q. I just draw the lines along with that here. This is along the P, this is along the Q. Okay, and this small portion it will makes at an angle of d theta. This is d theta. Okay, so consider small portion PQ subtending on angle of d theta at the center. It is with respect to center, at the center. So now if T1 and T2 are related to AB, RKB, then if you consider PQ, what are the forces we need to consider if PQ should be equilibrium? Okay, those forces first we need to draw here. Okay, so PQ is in equilibrium under the following forces. Okay, now I'll see what are the forces acting here. Okay, see, since T2 is there, along the P one tangent, one force it will comes, that is this in this point, this is in this direction, because T2 it will pulls, this will note as T here. Okay, so along Q, that is on the tangent to Q, one more force is acting, that is called here also T, because here T1 it is pulling, same portion Q is also pulling, T2 here pulling, so same portion it will be pulling here, that is T. Then any other forces? One is the normal reaction here, the normal reaction R, it will acting in this direction, this is normal reaction. What are other forces? So one more force it will be acting, that is frictional force. Frictional force exactly perpendicular to the normal reaction. It means here, this portion, this is F, frictional force. What is the formula for frictional force? Mu into R, right? This is reaction R, mu is coefficient of friction. So these three forces here this is T plus delta T. Why? Because here tension is more here in tight side. So that's why T plus delta T here it is acting. But in the slack side it is T, it will be acting. Okay, these two forces, one more is the reaction and one more is frictional forces. These four forces will be acting in the curve in the small portion PQ. Okay, therefore what is the first force here? That is tension T. First tension T in belt at where? At P. At P. What is the next force? T plus delta T, that is tension T plus delta T in belt at point Q. At point Q. Next, what is the next force? Normal reaction. C, normal reaction R. Okay. Next, what is the next force? Frictional force, right? Frictional force F equal to mu into R. Okay. These four forces acting in the small element PQ. Now what is the next step? If you want the equilibrium, PQ should be equilibrium, what we need to do? We need to resolve the forces horizontally and vertically here, right? Then only it will become equilibrium here. Okay. Now next step, resolving forces horizontally. Okay. What are these forces are there? We need to resolve horizontally. How we will go that? First I'll check what are the forces. Okay, I'll draw here separate free body diagram. Here one R, I'll draw here. This is R in the right side direction. R. Okay. Then I'll write F equal to mu into R, vertical. Exactly it is in vertical direction. I'll write one more here. It will be F equal to mu into r. This is one vertical. Okay. Now come to the T. I'll go here at the point P. T is there. How the direction is? See, this is right. This is T. Now resolve this into horizontal and vertical components. I am resolving here. See here, one arrow goes like this, one arrow goes like this, right? Because in this direction it will go. So what is the angle here? Angle is here d theta is there full. It is half. Half is d theta by 2. Similarly here also it will make at an angle of d theta by 2 here. Here d theta by 2, and with respect to vertical here also d theta by 2. So here I am getting this angle is d theta by 2. Okay, this angle. So can you tell me what are these horizontal and vertical forces here? If this is the T, this will be T into sine d theta by 2. Right? And how about this one? T into cos d theta by 2. You need to resolve. Resolve T, one is horizontal, one is vertical. I resolved here. T into sine theta by 2, T into cos theta by 2. This T finish. Now come to down force. T plus dt. This is the slack side force. I'll draw here. See here like this, right? This is T plus dt, right? T plus dt like this. Now I'll same split here. One is vertical component, one is horizontal component. This arrow mark is like this arrow mark is like this, right? Because in this direction. So what is the angle here? This is same, d theta by 2. This is d theta by 2. So now with respect to this, what is the horizontal component? T plus dt into this is sine, right? T plus dt into sine of d theta by 2. This is horizontal component. And how about this one? T plus dt cos of d theta by 2. Okay. So finish. These are the forces. This is one vertical, this is one horizontal, and T at the P I resolved into two components. T plus dt at Q I resolved into two components. Now resolving the forces horizontally. Check only which are the horizontal forces are there. Resolve left and right. Equate. First I'll go right side. Right side is what is the force here? R. This is the R. R equal to R. Any other right forces are there here? No, this is in left side. This is in left side. Okay. So no right side. R equal to, now go to left side forces. Here no, here no. And what is this one? T into sine of d theta by 2. Right? This is left side. Which is one more? Here. Here left side. This is plus T plus dt into sine of d theta by 2. Right? Any other horizontal forces? No. 1, 2 and 3. Only these are the horizontal forces. Now simplify this one. R, see here, theta by 2 is very small. This is theta. Theta by 2 is very, very small because we have taken very small portion of the belt. D theta by 2 is very, very small. So since d theta by 2 is very small, therefore sine of d theta by 2 is nearly equal to d theta by 2. Okay. Substitute this here. What is the R now? Therefore R equal to T, this is d theta by 2, right? T into d theta by 2 plus T plus dt into, this is d theta by 2. D theta by 2. Okay. Now I am resolving and I am simplifying further this one. R equal to T into d theta by 2 plus T into d theta by 2 plus this is dt, right? T into dt, sorry, this is t into dt plus dt into d theta by 2, right? dt into d theta by 2. So again neglect this one because dt and d theta are very small. This you need to neglect. Okay, so r equal to t and t, this is 2 times t d theta by 2. Therefore finally we will get t into d theta. Call this one as equation number 1. These are horizontal forces we resolved now, and we will get this equation here. Now what is the next condition to be equilibrium? Resolve into forces into vertical components. Now resolving forces in vertically, okay, vertically. Now come again here. What are the vertical forces? One here is there, upper side. First we'll go upside forces. This is F, that is mu into R. I'll directly write F equal to mu into R, that is mu into R. This is upside. Any other upside or upper side is there? One here is there, right? That is t into cos of d theta by 2 plus t into cos of d theta by 2. So any other upper side forces? Here no, here downside is there, right? So finish. Now equal to, come to downside forces. Here no, here no, here nothing, here, come here. This is only one force is acting downward here. That is t plus dt into cos of d theta by 2. Okay. Now again here d theta by 2 is small. What will be the cos of d theta by 2? It will be equal to 1. Why? Because if d theta is very small, it is almost equal to near to 0. Near to 0, very small means. So cos of 0 is 1. Cos of 0 is 1. But here in this case, if you take the sine component, sine of 0 equal to 0. But we should not take 0. The d theta by 2 is very, very small. We need to consider d theta by 2 as the value. So that's why here we are taking sine of d theta by 2 is nearly equal to d theta by 2. But here cos of d theta by 2 is nearly equal to 1. Okay, right, I'll write here, since d theta by 2 is very small, therefore cos of d theta by 2 is nearly equal to 1. Why? Because cos of 0 is 1. Here we should not take sine of 0 is 0. Because d theta by 2 is some value is there. That's why we need to consider d theta by 2. Okay. And now substitute this one here. Therefore, substitute in this equation mu into r plus t into 1. This is 1 equal to t plus dt into 1. This becomes 1 and this becomes 1 here. Okay. So again simplify, mu into r plus t equal to t plus dt. What we'll get here? Therefore this cancels here. R equal to dt by mu, right? So call this equation as 2, equation number 2. Now from equation 1 horizontally we resolved, we get r equal to t into d theta. From equation 2, if we resolve vertical forces, we will get the r equal to dt by mu. Now we can equate 1 and 2. Equate 1 and 2. Okay, equate 1 and 2. So what we will get? T into d theta equal to dt by mu. Dt by mu here. Okay. Okay, now separate the variables. How we will get here? That is mu into d theta equal to 1 by t into d theta, right? Into dt. I am separating the variables. Okay, what is the next step here? Now, if you consider the small portion of PQ, we will get this equation. Now we need for whole arc, AB, okay. So for AB we need to integrate, right? Now integrate above equation with AB with AB here, okay. AB, arc AB, right? Arc AB. How we will get here? Integration of 0 to theta. This is full theta, right? I started from A to B, 0 to theta. Integration of 0 to theta, mu into theta, dou theta here, okay? Equal to, what is the next integration? That is here T2 to T1, right? T2 to T1, because starts from here T2 and T1, that is T2 to T1, 1 by T into dou theta, okay. This for whole portion AB, we started. This is T1, T2, okay. Now again further simplify, we will get, why we need to integrate from T2 to T1 because the follower rotates in clockwise direction, so we need to consider first T2 then T1 here, okay. This is T2 slack side, this is T1, so that's why I wrote here, I started T2 and lower limit and T1 is upper limit here, okay. So now simplify further, how we'll get here, that is here mu, if you take outside, what is the integration of 1 is the theta here, that is mu into theta. Even if you substitute lower limit and upper limit, we will get theta here, okay. Theta minus 0 equal to what is the integration of 1 by t here, that is log to the base e, that is t. This is T2 to T1, okay. Again simplify here, mu into theta, that is log to the base e, T1 minus T2, upper limit minus this is log to the base e, T2 here, okay. Upper limit minus lower limit here. This will be equal to log of a minus b equal to log of a by b, that is log to the base e, T1 by T2. This is mu into theta, okay. Therefore what we need, the T1 by T2. How we will get the ratio of belt tensions? Because the headline is we need a ratio of belt tensions, T1 by T2 equal to e to the power of mu into theta here, okay. This is the one equation, standard equation, T1 by T2 equal to e to the power of mu theta. One more equation you can use, if convert log to the base e, in terms of log to the base 10, how we will get here this equation? You can also simplify this one, that is mu into theta equal to 2.3 log to the base 10. This is log to the base e, this is log to the base 10, T1 by T2 here, okay. This is also one of the standard equation. If you want in log to the base 10, you can use this equation. If you want log to the base e, you can use this equation, or you can use this also equation. This is also one of the standard equations here, okay. This is the one standard equation for ratio of belt tensions in terms of mu and theta. What is mu? Mu is coefficient of friction. Between what? Between belt and pulley, right? Belt and pulley. See here whatever we are getting between belt and pulley, the coefficient of friction is mu. What is theta here? Theta equal to, so the angle of contact. So here we will get one more angles here. What is alpha here? Alpha. So alpha is with respect to vertical we are getting here, right? That is the alpha, okay.